Get it? All right. Is the audio bar going la 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 la? Okay, excellent. I will start. Ahem. Hem. Hem. I need a whistle. No? All right. Bullhorn? One of those air horns, the wonk wonk. I think no. I almost bought one of those the other day. I should have. I will begin. Ahem. Dear Heavenly Father, we thank you for this day. I thank you for these students, most of whom are not talking at this point. Help us to have a good day and to glorify you what we do, Lord. In your name I pray. Amen. All right. So let me start with a discussion. So first of all, the quiz will be at the end, which means that some of you will finish the quiz and then go on your merry way. There are 2 questions on the quiz. I'm going to let you have your notes open this time. In the future, here's the deal. For the quiz, you're allowed 1 page. All right, so you should try to keep a page as you go, which has, the most important formulas that we have. That page should eventually grow into the sheet that you take to the test with you, right? So it could be the green one, or it could be the green one with extra stuff. It's up to you. But my larger point is there's no need to study for the quiz right now. You should try to focus on what I'm doing because in the long, in the bigger picture of things, you need to understand what I'm doing right now. All right. So the quiz is relatively small points. Not understanding what I'm doing today will end up being bigger points later. So I think the saying goes, don't cut off your nose to spite your face or something like that. I don't know. And why is there a fly in here? What is that? Anyway, sorry. I'm not imagining that fly. That's a real fly, right? Okay. So let's talk about force of friction. I need to talk a little bit more about it because I want to talk about static versus kinetic. And so here's a picture. We can graph. All right, this is the force of friction. All right. The force of friction, and here's what's possible. So the situation is something like this. So this right here would be like, this up here is mu sub s times the, oopsie. I used to use n for the normal force, so I slip back into that at times. My apologies. If you look at my solutions from Physics 231, many of which are relevant, right? Because calculus it's calculus-based physics, right? But if you look at what 231 actually has in it, I don't know, 70, 80% of what we do in Physics 231 has not an ounce of calculus in it, and it's the same content as what you're covering right now. So, those things I have written are not worthless to you. But this right here would be mu sub s times the normal force. So here's the deal. We have 0 less than or equal to the force of static friction. So the force of static friction is anywhere between 0 and this like maximum amount of static friction possible, which is mu sub s for static times the normal force. So that's the situation. I illustrated it last time with this chair. Do it again. Ow. So I could poke it like so. Wait a minute, let me get in the frame. I'm now in frame. All right, so if I poke it with a certain amount of force, it doesn't move, right? It doesn't move. We're in the static region, and then all of a sudden it'll start moving. That right before it starts moving is the maximum force of static friction that the legs of the chair on the floor can push back on me with, right? And that's proportional to the weight of the chair, which is the normal force in this case. Unless I was poking like, if I was pushing like this, then the normal force would be larger because some of the cane force is leading to a larger normal force, right? On the other hand, if I was to do like this, well, the other trouble with that is then I'm going to turn the chair over, and that's a chapter in the book we don't cover, so let's not talk about that. Chapter 11. If you want to learn about tipping chairs over and that kind of equilibrium, you should probably take the statics course that the engineering department offers, yeah? All right. So my point is chair not moving, chair not moving, chair not moving, chair not moving. The maximum amount of force I can push on the chair without it moving, and then all of a sudden something happens. Chair starts moving, then the force of friction drops back to like this. And so that drop moving, and then this is the force of friction kinetic. And that is just equal to mu sub k times the normal force. So this is the way friction works. It's 0 all the way up to the breaking point, and then once we enter the kinetic region, it drops back to a lower value. Now the specific values of mu sub s and mu sub k, that depends on the material we're talking about, all right? So trying to remember, I don't remember any off the top of my head. There's a table in your book, right? Oh, I think this is not, this gone everywhere, all the way around? Everybody got this? Oh, okay, wow. I guess we can go home now. Just kidding. All right. It's tempting to leave this room. It is unpleasant in here. But we should do some physics. Let's do some physics. Whoa! A little quiz there. Put that over here. Save it for later. Do you guys happen to know where I haven't looked this up recently. But I think if we look in the index, we can find it. Let's see here. Coefficient of kinetic friction, page 93 to 94. It's probably there. Yeah, also the static. So page 93, 94 in this book has got the table I'm looking for. These things are experimentally determined, right? I can't derive them using basic principles or something. Oh, here we go. So here's a table 4.2 or 4-2. We've got wood on wood. Wood on wood. Here's your mu sub s. Here's your mu sub k. So wood on wood, static coefficient 0.4, kinetic 0.2. I'll just write a couple of these out, guys. Ice on ice. That's like literal ice. We're not talking about diamonds. Let's see here. 0.1, 0.03. I think that is also vague because, ice is really different when it's like a little bit wet versus not like a little bit wet. So I don't know what kind of ice on ice that is. Yeah. Metal on metal. I don't care about that. Let's do rubber on dry concrete. Rubber on dry concrete. That would be interesting. That's something we, going down the highway. So rubber on dry concrete, mu sub s is actually 1.0. Wow, that's big. And on kinetic coefficient is 0.8. Let's see here. It's got, I don't know how to say this, synovial joints? Did I say it right? Kind of. Yeah, so human limbs, the coefficient of kinetic or static friction is about 0.01. Unless you have certain medical conditions, in which case it could be higher, right? Yeah, I guess. Either we have surgery and stuff. Teflon on steel in air is about 0.04.
What page is that on?
This is page 93 I'm reading from right now. Rubber on other solid surfaces is... So just to give you a sense of thing, rubber on other solid surfaces has a static coefficient of friction somewhere between 1 and 4. And the kinetic is just 1. Okay, I wanted to put this out here. So one of the interesting things that I should mention, just as a kind of point of general You can apply this to your life, I suppose. Rubber on dry concrete, right? So if your car is driving and the wheels are not slipping, right? If they're just lying down on the road, as the wheel turns around, it's actually not in kinetic contact with the ground. It's actually just lying flat. And as the wheel turns, it lies flat on the ground like that, and it pushes forward. So despite the fact that cars are moving, it's actually the static situation if the wheels are not slipping on the ground. So if you're driving a car and rubber, wheels on your car rubber typically, and you guys have cars with metal wheels? Probably not. So, rubber wheels on dry concrete. If you, were to hit the gas so hard that you spun the wheels, your coefficient of static friction would be 0.8, which means that you would actually not be able to speed up as fast as you would otherwise, right? So and then it's a more complicated story with like drag racers and stuff, right? There's more that goes into that. You can read articles on that, but anyway, just a comment. So let's look at an example. Now, the larger point here is I don't expect you to know the coefficients of static friction. I'm not like saying, oh, you got to memorize these. That's not my point. In a given problem, if there's friction, I will provide the mu sub s and or the mu sub k, and then it's your job to use them to analyze the problem, okay? So here's an example. Suppose we got a tabletop, and we've got a wooden block, and the table is wood. All right, and over here we've got a pulley, which is made of, well, I don't really care, whatever. But the pulley's got a string, and off that string hangs a mass, like so. All right, and so what I want to ask the question is, if the system at the start is not moving, all right, starting from rest, let's think about some different masses. Let's see here. Suppose we just take equal mass. Suppose this is M1 and this is M2, right? What's going to happen after we let it go if M1 is equal to M2? So what would the tension force be? This M2 is pulling down on the string with a tension of what? M2G, right? And we'd be pulling the wood and the top with a M1G, right? What's the maximum force of friction? What's the maximum static force of friction that's possible from the wood on wood contact, right? So the maximum force of friction here, force of friction max would be M1G, right? Because that's the normal force, right? This is the normal force. Can't spell. Normal force on M1, right? Normal force on M1 is just M1G in this case. And so the maximum force of friction is M1G times what? Times this right here, right? Times 0.4. So in the situation that we had these masses were equal, all right? If the masses are equal, I can put a number in if you'd like. Do you want me to put a number in? Yeah. All right, sure. No. M1 equals to M2, let's say 100 kilograms. All right. So the question is, here's the complete question. You have the situation, wood on wood, pulley, masses equal, hanging by a stretchless rope over a frictionless pulley. What happens, right? Now, it's possible in a different situation, right? If mass 2 was small enough, it wouldn't move, right? If the mass 2 was small enough, there wouldn't be enough force to overcome the force of static friction, right? In fact, you can see from right here, if mass 2 was like only 20% of mass 1, there wouldn't be enough to overcome the force of friction, right? But if they're equal, there is enough force to, if the masses are equal, as I said here, there is enough force to overcome the force of friction, it's going to start sliding, which means that we're in the kinetic region, right? And so then we can analyze it with Newton's laws. So let's do that. We draw the free body diagram on M1. And it looks like, oops.
Mr. Cook?
Yes?
So the force of friction is the opposite direction, and the static is when it starts going
The force of friction is always opposite the potential direction of motion.
So then where does kinetic energy come into play? Is that
Kinetic energy comes into play after test 1. So kinetic, but since well, okay, getting back to my point again, this is M2G, right? Which means that the tension is equal to M2G, which means that we're pulling with M2G this way, right? So as we look at the M1 block, we've got two things going on. We've got the tension force this way, which is, by the way, equal to M2G. And we have oh, I'm sorry. That is not correct. Why is it not correct? When is the tension equal to M2G? That would be in the equilibrium case, right? If the box is falling, it's not in equilibrium. There's an acceleration there. So what do we have to do? We should write M2A is equal to M2G minus the tension force, right? Since A is not 0, it doesn't have to be the case that M2G is equal to T. So, now, when would the tension be M2G? That would be when the box is not moving, right? If we're thinking about static equilibrium, that's okay because A is equal to 0. But we've already concluded that we're not in static equilibrium, right? The box is falling, we've got acceleration, so let's treat it as such. Let me fix this here. I've been selling you a bill of goods for the motion part anyway. This is tension goes this way, tension goes that way. This is moving. Can't do that if it's moving. All right, let me finish my my free body diagram for M1. I've got the tension going that way. My friction force goes opposite the motion, right? And the force of friction is mu sub k times the normal force. And what about the vertical direction on M1? What's going on there? What are the forces? Yeah, and which mass? Right, M1G. And this one, of course, is the normal force on, I mean, to be specific, I guess there's no ambiguity. Can you talk about the normal force on M2? That wouldn't make sense, right? It's not sitting on a plane. We wouldn't talk about that. So let's just say F sub n. Anyway, there's no other things going on in the vertical, right? So like if I was to say M sub, I mean, to be specific, that's A sub x, but M sub AY is equal to 0, and that's equal to the normal force minus M1G. So you see, there is no acceleration of M1 vertically, which means that the normal force and the gravity force have to balance, and the normal force is the weight in this case. Right? Okay, so then what? Looking at the horizontal part from M1, we see that M1A is equal to what? Which direction have I taken A to be positive? As soon as I write down this equation over here, I've made a choice, right? This makes a choice about the direction of A, yeah? When I write that, that means that the falling motion is counted as positive, right? So, which is positive, the tension or the friction force in this system of the tension's positive, right? So I should say M1A is equal to tension. Yeah, minus the force of friction, right? But we're in the kinetic region, and we just figured out the normal force is nothing more than m1g. So this is actually tension minus, what do we got? Yeah, now we're moving, so we use 0.2. 0.2 m1g. So what I'm going to do is I'm going to put these two equations on top, one here, one there, so we can see how to do the algebra a little bit better. Yeah? I guess I've kind of forgotten to tell you what the question is, right?
Yes.
Why do I do that? Yeah, I want you to create the question. That's one way to look at it. No, it's because there are many, many different questions which come from this same analysis, right? There's not just one question to answer. There's there's a couple dozen questions that you could create from this one example, right? Here's a very common question you could ask, though. What's the acceleration? First, part A, does it move?
Yes.
All right. Part B, what's its acceleration? Part C, what's the tension in the rope? All right, so let's try to answer that ABC question, just to make it more concrete for you guys. So we're almost there. We've made our free body diagrams, right? Figured out it's moving. Now I want to find the acceleration. So what I'm going to do is I'm going to add those equations just like we did last time, right? Add these equations, what happens? We get m1 plus m2, a on that side. On the other side, we get m2g minus t plus t minus 0.2 m1g. The t's cancel, and we're left with m2 rather, minus 0.2 m1g. And so we can solve for the acceleration. What's the acceleration? m2 minus 0.2 m1 parentheses g divided by m1 plus m2. So what was my m2 and my m1 were both 100? So we got what? We've got 80 kilograms over 200 kilograms times g. So you could state it in terms of g. We'd have, what is that? (0.4g), is that right? So the acceleration is 0.4. It's 40% of gravity, yeah? Of course, we could also write that in terms of meters per second squared. What would we get?
Did you multiply the 0.2 times m1 in the equation?
Well, yeah, so this is 100 minus 0.2 times 100. So that's 100 minus 20 is 80, I think.
Yeah.
And then 100 plus 100 is 200. So that gave me 0.4. 0.4 times 9.8. Yeah, 3. Stupid calculator gives me exact fraction. Worthless. All right, 3.92 meters per second squared. Now let's just stop and, common sense checkpoint. Does it make sense that the box is not falling faster than, it's falling less than free fall, right? If I just take the marker and drop it, how fast does it accelerate? It'll be okay, don't worry. Ignoring air friction, 9.8 meters per second squared, right? It's falling slower. Why? Because the friction force of the wood on wood M1 is slowing it down, right? It's a drag. It's slowing down. All right. What's the tension? How would you figure out the tension then, once you figured out the acceleration? That was my final question here. What was the tension? Yeah. Aha. Now, so Megan says, go back up here. That one? Or the other one? You go either way, right? So this one, if I solve that algebraically, that gives me T is equal to M2G minus M2A, right? Oh, hey, look at that. I can factor M2 out, and it's M2G minus A, right? But we just figured out that the tension then is M2 times, well, G minus 0.4 G. So apparently it's 0.6 M2G. The tension is actually 60% of the weight of M2. Let's see here. 0.6 times 100 times 9.8. Oh man, what did I just do? I found a new button on my calculator. It was not helpful. Ah! Fingers are not working. Not a good sign. I get 588 newtons. So there you go. There's the tension force in this situation. Tension in the string is that. Any questions? Yeah. Oh, I just 1 minus 0.4 is 0.6. I just factored out the G and thought about 1 minus 0.4. You calculate it another way if you want to, but we should all agree on 588 newtons.
Is that for M1? Or is it
That's the tension in the rope. What was your question again? I mean, if we had if we solved this other one, how would this work out? T is equal to, uh-oh, now you guys got me worried. How'd that happen? What? Because you got a different thing if you solve the other equation, didn't you? That doesn't make sense. This.
We did 0.4 down here, and then it would be 0.2. You see where the formula is? It's T minus 0.2, and then we did 0.4 down here.
Where did I do 0? That's from this over here. That's the acceleration. I'm using, this is A. I just put A there. What's more concerning to me is when I solve for T here. Oh, I wonder if I think I did the algebra wrong, guys. No, did I? No?
No.
Oh, wow. I'm sorry. It looks to me like this is M1A plus 0.2. Oh, I'm an idiot. Look, how's this work out? What's M1A? So this is what? M1 times 0.4 G, right? Plus 0.2 M1 G. So this is still M1 times 0.6 times G, which is still 588 newtons. All right. I'm sorry. I had talked myself in my mind into that being 1.2 M1 G, which would be different. But it's the same. It doesn't matter which equation you solve. You should get the same tension. Yes, Megan? Look. This is G minus 0.4 G. So if I factor out G, that's 1 minus 0.4 times G. But 1 minus 0.4 is 0.6. That's where that came from. So.
That's the 0.6 times.
What? It's okay. All right. So here's an example with both kinetic and static friction. We can have both in a problem. You have a decision to make. Does it move? Does it not move? Right? Similar questions can be asked for, like a box on an inclined plane, right? Given the kinetic and static friction, you can ask the question, does the box slide or not, right? So I'm going to now show you a standard example about Newton's third law. Whoa, do not walk into the cloud of the stuff. It's not good. All right. So I'm going to give an example. So this is to illustrate the third law. Standard example. Here's the question. You've got, here we go, M1 and we have M2. All right? To keep things relatively simple, and I don't think it might not change anything actually, let's assume that we're on a frictionless plane. All right? Then, what we're going to do is we're going to put Mr. Top Hat over here. And he's going to poke M1 horizontally with his cane. Like so. All right? And then the question is, well, there's a couple questions I have. If he pokes the M1 horizontally with his cane with a force of F sub 0, right? Here's the questions. A. What is the acceleration of the system? Right? Question. What's the acceleration of the system? B. What force does M1 push on M2 with? In other words, what is the contact force? Between M1 and M2. All right. Yeah, frictionless. Right. We could add friction, but first we should try to understand this, all right? So now we have two masses, all right? Well, we had two masses in my last example as well, right? But now we have two masses, and so what we want to do is look at identify the forces acting on each mass and write down Newton's second law. That's how we do it. Newton's third law comes into play in the contact force. What Newton's third law says is that the force of M1 pushing on M2 is equal and opposite to the force of M2 pushing on M1. The contact forces from one on the other or the other on the one, they're equal and opposite. That's the third law. So let's do it here. M1. And I'll draw them up here. Well, I'm going to draw them down here actually so you can see it better. So here's M1. M1. So first, you got the normal force, Fn1. You've got the force of gravity, M1g. These don't actually play any role because I'm assuming frictionless. So those just cancel out, and they say that the acceleration relative to the plane of mass 1 is just 0. It just stays on the plane. All right? It's the horizontal that's more interesting. Horizontally, we have F0 pushing on M1, like so. I'll draw it over here, because we like to think of all the forces emanating from a single point when we do the free body diagram, right? Yes, physically, F0 is pushing on the left side of the mass, but when you draw this free body diagram, you want to put them all from one central point to visualize the addition of the vectors, okay? So this is F sub 0, which is the given force. And then there's this normal force. There's the push-pull, all right, which I'll put a green illustration of here in just a second. we have this one. So this is the force of, I'll say 1 comma 2, and equal and opposite, we have the force of 2 comma 1. You could, I mean, you know what? That's kind of annoying. Let's just use a big C for contact, if that's okay with you guys. Contact force. C for contact. So the contact force is like this. Now, the contact force and F sub 0, they do not cancel out. They don't cancel out. We're not in equilibrium. It's moving, right? So the way to understand the relation between the forces is Newton's second law. So we have Newton's second law, and Newton's second law for mass 1 is just that m1a is equal to F sub 0 minus the contact force. All right? Step number 1. Now that we have understood that, we draw the free body diagram for mass 2. Let's draw a picture. Here's, oh, not to scale. I mean, it doesn't really matter if your picture's to scale, not really. Okay, so again, we have the normal force for the second mass. We've got the force of gravity for the second mass, m2g. Those are equal and opposite and cancel out because we are in equilibrium with respect to the vertical motion to the plane, right? It's staying on the plane, there's no vertical acceleration. Those balance out. Horizontal, not balancing though, right? Horizontally, now does F sub 0 push on mass 2? It does not. The only thing that's pushing on mass 2 is what? The contact force, right? So in fact, to be more precise, this one was that one, yeah? But the force of m1 pushing on m2, if I could use some color coding here. I'll use brown. Again, these two forces are equal and opposite because of Newton's third law. There's just the contact force like that. They're not the same contact force, right? They're the same magnitude, but they have opposite directions. They're what's called the third law pair, right? It's Newton's third law in action. And so what's Newton's second law for mass 2 then? Well, we have decided that direction's positive when we wrote this down. So, well, that's one of the things is, do we need separate accelerations for mass 1 and mass 2? They're stuck together, right? So they share the same acceleration. So that's something, if you're very abstract, you might think about different accelerations for the different masses, but we don't do that. So m2a is equal to c. That's Newton's second law for mass 2. So what does this give us? 2 equations in 2 unknowns. What are the things we don't know? We don't know the acceleration, and we don't know the contact force, but we can figure out both of them by combining these equations and solving, right? So what happens? So, I said find the acceleration. So now that's the physical setup. After this point, we do algebra. So it's always algebra. Algebra, algebra, algebra. All right, but it's not that bad. I mean, so we have m1a equals to F sub 0 minus c, and I'm just copying these down again, guys. m2a, so you can see it where I'm working, okay? So how would you solve these 2 equations for, I mean, if I want to find a, what do I do? Yeah?
Can you rearrange the first one so it's equal to c and then sub that?
Oh, okay. So you say solve this one first. This is c equals to what?
M1, or, yeah, sorry, it would equal M1a minus F1. Or, minus, sorry, yeah. Minus M1a plus F1.
Okay, so, right. So no need to hurry, just think through it, right? That's it. Everyone agree?
Yes.
And then, like you said, we also know that c is equal to m, so that's equal to m2a. And that's great because now we have one equation, one unknown, so we can solve for A, right? So solve this for A. That would give us f sub 0 is m1a plus m2a. So we can factor A out. So f sub 0 is m1 plus m2a times a. So my acceleration is f sub 0 divided by the sum of the masses. That's the answer to question A. What's the acceleration of the system? Now, some of you, maybe you had physics in high school, maybe you took AP physics, I don't know, whatever. I bet you knew that already. Show of hands, who knew that the acceleration was just the force divided by the sum of masses without going through this analysis that I just did? Okay, well, one or two of you. I sometimes I usually have students interrupt me mid-calculation and go, hey, why are you doing all this? You just take the masses, add them together, and divide it into the force. That gives you the acceleration. The idea that those students are using is called the particle model, which is that instead of thinking of mass 1 and mass 2 as separate entities, you can think about them as a combined thing, big M equal to m1 plus m2. It's just like a single particle with the combined mass, and so if I want to find the acceleration of that single particle, I just take the force divided by the mass, which is m1 plus m2. That's not wrong, that viewpoint. So you could find the acceleration more quickly in that way. But then you'd have no understanding of what the contact force was between the masses, right? So what's the contact force then, now that we figured out the acceleration? Right, this is C. So C is equal to m2a. What was A? Was that, right? So it's m2 f sub 0 divided by m1 plus m2. So there you go. That's the contact force, the force with which one box pushes on the other. Now, you know, we could put numbers in this problem, but I don't think that really changes the analysis that much, right? Maybe it makes the algebra less scary. I don't know. Let's think about this contact force equation. What would happen if the boxes had equal mass? How much contact force would there be of the second one on from the first? What happens with that equation? You'd have half, right? So if you actually have equal masses, then there's actually a half of the contact force pushing on the second box. So I think of it this way. I think of the first box as using up like half the force and then sharing the other half of the force with the other box. That's how I think about it. Anyway. You can add a third box to this and ask about the contact forces between both of the boxes. But the thought process remains the same. You just then have 3 Newton's laws and 3 equations and 3 unknowns, and you can do that.
You said if it was the same mass, it would be half of the force?
Uh-huh. Half of the contact force would be half of F naught. See, because if these are equal, then you have m over 2m, which is just a half. It's F naught over 2 because the m's cancel. Yeah. Okay, well, listen, so what I thought I should do, and we still have like 15 more minutes before I give you the quiz, is I wanted to at least get started on gravitation, all right, or possibly circular motion today, because the test is going to be here before you know it, and if we at least start talking about gravitation right now, it has a little bit longer to kind of like settle in, and you have a better chance at doing well on that on the test. So we will have more time next week for homework questions about all this stuff, all right? But I think for the next 15 minutes, I'd just like to give you a brief introduction to Newton's law of gravity. How about that? And circular motion. Mwah! Oh no! So let's start with the circular motion. So we have the net force, right, is equal to ma. This is Newton's second law, right? But we really only think about this in terms of straight line motion, right? In here, at least. There's one other case of motion which is simple enough that we have equations that we can deal with in here, and that's circular motion. So for circular motion, we have the following. We have that mv squared over r is equal to the force, the centripetal force. Or center-seeking force. So in other words, if I have motion in a circle, right, and I want to keep the motion in a circle, this is mass m, then to keep something going in a circle like that with constant velocity, all right, well, actually, even if the speed isn't, not constant velocity, that's crazy. Can you have constant velocity in circular motion? No, because the direction is always changing, right? So, but we could have constant speed circular motion. For example, well, relatively constant speed. Here's one. So like here, right? You can have circular motion. What keeps the yo-yo going in a circle? What would happen if I cut the string? Yeah, we go back to Newton's first law, right? That constant rectilinear motion. But there's a tension force in the string which is keeping it going in a circle, right? That tension force is the centripetal force I'm talking about, and that must be equal to mv squared over r. So if I go faster, larger tension force, right? I can feel that. I don't know if you can feel it. Can you feel it? Tough crowd. So I'm not a yo-yo master, but this used to look better. Then my children got their hands on it. I don't know. It's missing its. It still works though, right? So anyway, this is. So if this is speed v, like this, then that's the formula. mv squared over r is the centripetal force. This is how we. This is Newton's law for circular motion, is what it is. Okay. That's it. Gravity. Gravity. Well, Newton put forth this hypothesis that gravity obeys an inverse square law. And in particular, what Newton said, he suggested, is that if you've got a mass 1, actually, and you got a mass 2, let's think of mass 1 being huge. Oops. All right. And sorry, circles. Circle's dead to me. So here we go. Here's mass 1. Then what Newton said is if you look at the straight line which connects these two masses, if you connect their centers of mass, whatever that means, I think you have an intuitive sense of what that means. If you connect the centers of these two masses, right, then what Newton said is that there's a force of gravity which attracts the two masses, right? And how does it work? Well, there's also a third law. Newton's third law comes into play. The force of gravity of m2 is pulling on m1. The force of gravity from m1 is pulling on m2. Let's just focus on m2, though. So there's a force of gravity that points along the direction of the line that connects them, force of gravity. All right? And what Newton said is that this force of gravity has the following form. The magnitude of it, all right, is equal to big G m1 m2 divided by r squared. And here, r is just the distance that connects the centers of mass of m1 and m2. All right, so r is this. And this is Newton's universal law of gravitation. All right, it's an inverse square law. I'll talk more about it next class, but I'm just going to give you this introductory example to it. So, you know, you can ask the question, like if we think about the Earth, right, and think about a satellite that's in a circular orbit, right? Then what keeps the satellite going in a circular orbit? Does it have little rockets that are like always firing it to keep it going in a circle? No, that's not quite it. It gets going at a certain speed and then it just keeps going around the Earth, round and round and round, right? Gravity is what keeps it going in that circular motion. So if I can draw a picture of that, over here maybe. Here's a picture of that, Earth, yeah? Not to scale, guys, not to scale. So, satellite. I forget how to spell satellite. Anyway, up here. I don't know. Anyway, the point is, this distance is the orbit. That's the radius of the orbit of the satellite, right? It goes in this circle round and round the Earth, right? Roughly speaking. And what is the equation that, what does physics say? Physics says that the mass of the satellite times the velocity of the satellite squared divided by, this radius has to be equal. What's keeping the satellite going in a circle? It's the force of gravity, right? So what we do is we say mv squared over r is equal to g, mass of the satellite, mass of the Earth, divided by r squared. So if you want to figure out what's the velocity of a satellite at radius r, we can do that, right? The m's cancel. And we get v is the square root of g, mass of the Earth, divided by r, I believe. Now what's the mass of the Earth? No, wait a minute, 5.94 times 10 to the 24th kilograms, obviously, right? And what's g? That is the universal gravitational constant. If I ever hit the right number of, it's in here somewhere for me. I don't remember what this stupid thing is. I could hazard a guess. 6.59 times 10 to the minus 11th. Okay, good. I'm glad I remember it right. 6.672, thank you. That gives me hope. I may yet remember other things in my life. 6.67 times 10 to the minus 11, though? Yeah. All right, yeah. And what are the units on the gravitational constant? Can we figure that out? Look at this. The units of g have to be the units of force times the unit of length squared divided by the units of mass times mass, right? In other words, it's a Newton meter squared per kilogram squared. That would be the units for the gravitational constant, which of course we could also write as kilogram meters per second squared times meters squared over kilograms squared. So I guess the units on the gravitational constant are they are meters cubed divided by seconds squared kilograms. Is that right? Sure. All right. Thanks.
It looks good.
It looks good? All right, well, let's do meters cubed times, divided by seconds, what did I say? Seconds squared kilograms. If you think about that, if you think about taking this, right, and multiplying it by a mass and dividing it by a distance, this unit will reduce to just meters squared per second squared, which is good. So if I think about the dimensional analysis here, it makes a lot of sense to me, because after I calculate this, I got a meters squared per second squared, I take a square root, I got a meters per second, which is the thing I'd like to see for speed, right? So So I think that's pretty neat. You can figure out the relation between, the velocity and the radius of a satellite orbiting with this simple bit of algebra. If you want the satellite to be in geosynchronous orbit, what would its velocity and so forth be? What would geosynchronous orbit be? Yeah, what is geosynchronous orbit? What's the Earth do? It revolves around its axis, right? So a satellite in geosynchronous orbit is always at the same position over the Earth as it's rotating. So if I'm the Earth and the satellite's the end of this thing, as I rotate, satellite's always in the same spot, right? So that's geosynchronous orbit around me, always the same position as I rotate. How long does it take for the Earth to rotate? 24 hours, give or take a leap year second stuff. So yeah, if we want this to be 24 hours for a cycle, what's the speed? V is equal to 2 pi, the radius we don't know, divided by 24 hours. Right? Yep.
Is the M8 plus 5.94 given?
Oh, I just remembered that from the dark recesses of my mind. We could derive that. We should talk about, that's just the mass of the Earth, but that can be experimentally determined, because we'll get back to that. But there's a way we can understand why that must be what it is, because we measure gravity to be 9.8 meters per second squared, the acceleration. So you can work backwards from that what the mass of the Earth has to be, because like this formula right here, this becomes well, if I think about M2 sitting here, right? If I look at the radius of the gravitating object, then if I look at M2 G, that would be G M2 M1 over R squared. So like G times M1 over R squared, that gives us the acceleration of gravity on the surface of this M1. And so because we can measure the acceleration of gravity on the surface, and we can, through other means, estimate the radius of the Earth, we can figure out what the mass of the Earth must be on the basis of this analysis. We should talk more about that some other day, though. But for the moment, it's just a number I looked up in a textbook. Yeah. Again, not something I'm expecting you to have memorized. It's something I would provide in such a question, yeah? So my question, so right here, this is the velocity for geosynchronous orbit, right? Why do I have 2 pi r over 24 hours? What's that coming from? Because if we go in a circle, 2 pi r is the circumference, right? And if we do that in a day, that's the speed of geosynchronous orbit. So then you can take that and you can combine it with this, right? And you can figure out what the radius is of geosynchronous orbit. See, because this would be equal to the square root of g times the mass of the Earth divided by r. At this point, this equation has only one unknown, the radius for geosynchronous orbit. Right? So we could, if we wanted to, we could solve that equation for r, and that would give us the radius for geosynchronous orbit. If I remember right, I think it's an altitude of about 22 kilometers. 22,000 kilometers, was it? I forget. What's the difference between altitude and r, by the way? This is on page 123 of the textbook, guys.